Welcome everybody to this webinar titled How can HFWorks help you to design an implantable antenna inside SOLIDWORKS? The agenda of our webinar today will be first an introduction about the software, and after this we'll talk about the model that we will use to do the simulation and to show you the workflow of the software, HFWorks. And at the end, we'll conclude by answering your technical question. So the model will be an antenna used for wireless biometry and just to send the information from the human body to a monitor close to the human body. The challenge of this antenna is the dimension. So the dimension, we have to respect small dimension, and we have to respect the standard frequency of this kind of application, which is low frequency around 400 megahertz. HFWorks is a full wave 3D software. It's fully embedded inside SOLIDWORKS. It means it's an add-in inside SOLIDWORKS. It uses SOLIDWORKS as a CAD to read the geometry. It's based on a frequency domain finite element method. So it covers the whole band of the high frequency, going from a few megahertz to some terahertz. It's also, it can be coupled with thermal analysis coming from the Joule effect. It is gold certified by SOLIDWORKS. It means to respect the highest integrity, and it is respect the highest standard of SOLIDWORKS add-in. So the how to simulate inside HFWorks any model. So first, we have to create the model inside SOLIDWORKS, or simply import your existing 3D geometry from another CAD. It can be SAT file, IGS file, XT file, or any other format. Second, we have to define the pre-processing steps. It means assigning the material to each body using HFWorks material, or also the user can create his own library. Also, we can do parametric study or multi-configuration study to play with the geometry. We have to create the mesh. It's an automatic process. Also, it is possible to control the mesh to get a final mesh on a particular region, the small gaps. And at the end, we solve to extract the different output parameters. It can be circuit parameters, it's like data points, data information, or 3D field results. So our antenna today will be the spiral antenna, this to be able to create very long antenna in a small surface. The dimension of the substrate is 2 centimeter per 1 centimeter, and the thickness is 1.65 millimeter. It's the material of the substrate is Roger with the permittivity of 10.3. And our antenna will be implemented inside the body between the skin layer and the muscle layer, and it is protected by a material. Here the antenna is inside which is called superstrate, just to protect the human tissue from any arcing or any short circuit. Let's now see here in the software in action. So this is our model. We created the model inside SolidWorks. So we have here 3 layers plus the air region. This is the air. Let me hide the air and change the transparency of the other layers. So this is our antenna inside the human body. And the antenna, as you can see, has some dimensions that we created here. And it's very useful to here to use smart dimension. Why? Later we will be able to drive any dimension, to change any dimension within the same geometry. It means no need to just work with another assembly. We can take the same assembly and play with the geometry, simulate with different scenarios, and we can compare the results to see what's the impact of any parameter on our output. So this is the model. Also, there is a nice feature inside SolidWorks which is called cavity. Just the cavity is function to subtract a part from another to avoid any interference. So this is the geometry, and you come here to HFWorks. So in HFWorks, we to solve any RF problem, just simply you create a study, which is called study here. It can be an antenna problem or S-parameter problem to compute the scattering parameter. It can be also a time domain reflectometry problem to see the impedance change inside RF structure, or resonance problem to check, to compute the natural frequency of any structure, any closed area using HFWorks. So our application today will be an antenna. So we create an antenna, and here in the interface we define just the properties of this simulation, such as, for example, the frequency band. So we can use discrete sweep or fast sweep. The difference is, for discrete sweep we solve the problem for each frequency one by one, and for fast sweep just we define our band, and here we define the number of points, for example 100 points, and based on the solution, here we can control the number of solutions. Based on the solution, we can just interpolate for the other frequencies. In general, always we start by the fast sweep to predict the band, the resonance frequency. After this, we can do another simulation to solve some frequencies inside the band. So here we'll define just our band. So for example, you can solve from 370 to 420 megahertz, and here you choose the number of points. For the meshing, you can here just use the default mesh. It's automatic process, no need to adjust any parameter, except here sometimes when you have curvature, circular forms, you can turn on accurate curvature to force the mesher to create a node each given value here of angle. For example, each 15 degrees, it will create a node. You can control the number of points. In addition to this, HFWorks can be coupled with thermal analysis as to predict the temperature distribution due to the losses in the material from conductor, lossy conductor, or from lossy dielectric material. Here the study is created as pre-processing steps. We have to assign the material to each body using our material library, or the user can create his own material. It's very easy. Just we right click on the part and we apply here from HFWorks material. We have hundreds of materials classified by category or by suppliers. For example, for the air, just simply we can assign air. For the body, we have three bodies. So for the skin, for example, we can come here to biological material and come to dry skin and choose the right material. Also, it is possible, for example, if you wanted to adjust any parameter, simply you edit the material and you will get access here to adjust any parameter. If you wanted to use your own material later for other projects, just you can here apply material, and instead of using HFWorks material, you can create your own material. So you can load existing material, or you can simply here, for example, we can create a new material, a new library, and inside this library you can define new folder and new category and a new material here, and we can enter manually the different parameters such as the permittivity, loss tangent, the electric conductivity, or any other parameter. Okay, so for this, just if you have, for example, any existing study, we can drag and drop from the previous study the material, for example, from here to here, just to copy everything. See here. As a second step, we have to define the two main information. The first one is the port. It means the feed points of our antenna. So first, let me just isolate my substrate. So my feed point, or my port, will be limped port, because I know that the impedance of the input port is 50 ohm. To force the impedance, just we can define here a limped port, and we select the entry port here, in between the two traces. So this is the port. It is an internal port because it's inside the computation domain, inside the air, and we defined here 50 ohm port. For the conductors, just because here we created split line instead, because there is no skin effect in this frequency, so just simply you have to define an imperfect conductor here, an imperfect conductor to the face of the trace on the substrate, and we choose here certain a material with certain conductivity. For example, copper can be this copper, and we can also add some roughness. Second or third point is to define the radiation boundary, or what is called absorbing boundary. So it means, because in the real life there is no truncation of the air around the structure, so we have to apply some boundary to avoid the reflection of the wave at the end of our computation domain, because it's infinite area, infinite air around. Just we have to select here radiation boundary and apply this radiation boundary on all external faces of our structure everywhere. Actually, I can copy and paste from the previous one. Okay, radiation boundary. So I'll copy everything. Now, as a last step is to create the mesh. So the mesh process is very easy. Just you ask, let me isolate again, substrate. So here you go to mesh setting, and you can adjust the parameters from here. Also, it is possible to apply mesh control if you have some expertise with the RF devices, you know that the maximum field is on the outer edges of the traces. So for this reason, you can select the trace, the faces, and you extract edges, all edges related to this face, and you can assign a very fine mesh just to make sure that the software catch everything and the results will be accurate. So let me just now show you the mesh. So this is the mesh, the substrate. Also, there is everything is meshed, but we can hide, show any part. So this is the model meshed, and this is the mesh details. So it's the total number of nodes, 31,000, and the total number of elements, 177,000 elements. And also you can check the more details about the mesh. So we have some number of elements related to each body. You can check here the number of elements, for example, on the substrate below or any other part. And after this, just you hit run to solve the problem. Once it is done, it is fast, so it takes just 1 minute for this example to simulate. When it is done, the software will create results folder. The results folder contains here numerical values of the circuit parameter, output parameter, and also we can make a 3D plot of any other quantity, such as the electric field or the magnetic field or the port field or the losses related to any body with certain lossy material. Let's check first the results table here. So we have the results table. We have frequency list here, the left side. So we solve it from 370 to 420 megahertz. And we can check in the right side the S parameter related to each frequency. We can check the normalized S matrix, impedance matrix, the port results, VSWR, and we can plot all of those quantities in 2D format. Come here and you create 2D format. For example, you can here select the S11 and plot S11 versus frequencies. So this is the resonance frequency is about 402.25 megahertz. At this point, we got minus 30 dB almost. And this is the list of the S parameters. We can also, for example, make another plot of VSWR. So this is VSWR, a minimum of 1.08 at the same frequency, the resonance frequency. So we can get the list. We can actually save the data points as Excel format or text format. Also, it is possible to save the plot also as picture format. It can be PDF, bitmap, JPEG format, or any other format. We can actually also plot the electric field on here. This is the electric field on the whole body. You see, this is it's normal to get a blue color outside because everything is inside the computation domain. But here to see inside, we can show on a particular part, and we can pick the part from the SOLIDWORKS tree here on the substrate, only on the substrate. And for example, I don't care about the other other bodies. So this is the electric field really in the substrate. I can actually control the input power. One, for example, and it's adjusted automatically the electric field based on. If you have more than one port, you can also play with the phase. You have the weight and the phase of each port. Actually, you can also animate the electric field versus phase to see the propagation of the wave. We can choose another type, another format field. For example, we can make here a vector format, and we can adjust the length and the density of the vectors. Actually, we can see also here what happened on a selected part. For example, on the here in the air part. So this is the field in the air. Actually make constant vector to see the small values. This is the vector in the air region. Not only here colors, also you can check the values of the field, electric field. For example, you can make 2D plot of the electric field, for example, on at a certain location, for example, from this corner to this corner, straight line with this resolution. Here you choose 51 points from point 1 to point 2, straight segment. And this is the electric field from point 1 to point 2. And we have here the list of the electric field, a peak in the middle of 65 volt per meter. So same thing can be done to see the magnetic field also. Also, it is possible to detect the location of the highest field by using isoclipping. Isoclipping is a nice feature to see the location of the highest field. Actually, you can superimpose with the gray model. So, for example, you can here choose your scale and just detect the location exactly of the highest field. You can actually superimpose, do multi-layers, and choose some values of field just to see what is the maximum minimum field in the geometry. Now, as post-processing and related to the far field, the far field is a post-processing also process. It means after solving the electric problem, we come here to antenna parameter, and we can create a new far field case, and we can control here the step of the phi and theta. We can actually also control the power, and that's we can here solve the problem at this solution. And once you do that, you will be able to create here a 3D plot, polar plot, or 2D plot of the far field parameters. So here we can right click, go to polar plot, 3D, and we can choose, for example, any parameter. For example, it can be the gain, it can be the radiation intensity, the RE field in X, Y, Z direction. It can be the efficiency of the antenna versus frequency. So we can here choose any parameter. Gain pattern. So this is the gain of the antenna at this frequency, and we can superimpose with the 3D geometry also to see the direction. It is expected that the direction of the antenna will be like that. we can actually make section view of this gain by using here 2D polar plot, and we can fix the phi and vary theta, for example, gain, and we can here check the gain or the directivity versus theta. This is theta angle, and you have the gain value. Another advantage of getting the solver inside the SOLIDWORKS is the parametric study. So by using the parametric study, you can change anything in the geometry. For example, here, just simply you can let me hide the layers to have access to the substrate. So here we can define a parameter. I already selected the parameter, which is the length of the spiral antenna. We can select any other parameter. Just you come here and you pick any parameter. For example, here this one or this one, or any other parameter. It can be also just a mate between parts. So you pick any one. You come here, and instead of creating a regular study, antenna study, you check parameterization. Parameterization, you can simply copy and paste everything from the previous study, the material, boundary condition, and you come to the to define your scenarios. Go to design scenarios. So I selected already 3 parameters. I can uncheck second and third one and keep only the length of the antenna, and I can here define a minimum, maximum value, and a step. So the default value is 5.5 millimeter. I can, for example, define a minimum 5, maximum 7 millimeter with a step of 0.5 millimeter and generate scenarios. So here we have 5 scenarios generated. I can rename the scenario name. Also, I can adjust, if I don't like this value, I can just simply type the new value here. And automatically the software will adjust the geometry according to the requested dimension and give you the results with the new design. So let me just share with you here. I already solved the problem using same length here. So I defined here 3 scenarios going from 5.5 to 6.5 millimeter. And after solving the problem, I got the results. So we can plot the S11 as parameter versus scenarios. So I have 3 scenarios, so I can add the S11 versus all scenarios. Add. There we go. So we have the S parameter. See, it affects the band, the resonance frequency. The green one is at 6.5 millimeter, and the blue one is at 5.5 millimeter. The original one was this dimension, 5.5 millimeter. So this is, it's very easy to use. No need to recreate the geometry or to redefine everything from scratch. Just simply you use here the parametric study. Same thing for the far field parameter. You can here come to make polar plot, and you choose. Just let me here. You choose here you select your frequency, you select your scenario, and you can check any parameter here related to a given scenario or a given frequency. So we have the frequencies, scenarios, and you can plot any quantity. A model. So as you can see, so we can solve easily any problem. No need to be expert in RF to solve an antenna problem, or it's not a headache as other tools to play with the geometry or to define material or straightforward. It's very easy to use, user-friendly interface, and it's very accurate software. It's just I'll conclude by just another feature, which is also very useful, just because just to not spend time to create a report. Automatic report here, you can prepare the plots that you want to show in the report. You come here to the reports and you generate a report. It can be in Word format, HTML format, and just you click here, okay, to generate a report. Actually, you can add some description, introduction. You can add, for example, model view with standard view, isometric, with or without mesh, and that's it. So you click OK, and automatically it will generate a Word report or HTML report, and you can share this information with your colleagues. So this will conclude our presentation of today. If you have questions, please just type your question in the web meeting chat box. It will be a pleasure to answer all your questions.